Hello there, and welcome to my video on slope fields. A slope field is going to be a collection of slopes along a lot of different points for a differential equation that is going to give you the slope at a given point. Now, real quick, so everybody understands what a differential equation is, that it would be something that says dy over dx is equal to some expression. I don't know, x. Okay, that's a differential equation simply because I have this thing here. Now, the slope field is going to identify the set of solutions for a family of solutions. Now, what does that mean? Well, let's say, for instance, that we have a differential equation. Let's just take the one that we have here and solve it for, let's get dy by itself. So that would be, I'll do it over here on the right side. So dy would be equal to x times dx. Well, what we've done is we've separated the variables. And at this point in the process, what we would do is we would take the integral of both sides. Well, the integral of, let me go back to my color here, pink. On the left side, the antiderivative of dy would just be y, and the antiderivative of x would be 1/2 x squared plus c, because we're doing an indefinite integral. And when we learned initially in calculus about indefinite integrals, anytime we would take the antiderivative of something, we had to include that constant for our family. That constant can represent any number. So maybe it's a positive number, maybe it's a negative number, maybe it's a whole number, maybe it's a fraction, it could be anything. It's just going to represent essentially vertical shifts up or down on the function. We're definitely going to have something quadratic, but where the C value is, that's up to what the initial conditions really tell us that it's going to be. So let's go ahead and take a look at our first example, where we have dy over dx is equal to 3x minus 2. So again, this is a differential equation, and we have here, this is our inputs, whatever they are, whatever value of x you want to use. And dy dx, those are our slopes at that input. That's why we create a slope field. Now, the slope field, we only take a little segment of it. We don't actually write the entire slope on the graph. So let's just see what that's going to look like. Let's take the leftmost value of x that we can have on this example, which would be a -2. Well, I'm going to take the -2 and I'm going to substitute it in for x. So 3 times -2 gives me -6, minus 2 gives me a -8. So essentially what that's telling me, particularly because I only have one input number, I only have the x values that I can input anything. Anywhere I have a -2 for x, I'm going to have a slope of -8. So on my slope field, I'm going to draw essentially a vertical line, because the slope of -8 is very steep, and we're not trying to be specific, particularly exact on here, especially because I don't have a straight edge or anything. But we're definitely not going to be able to count a slope of rise over run of 8. So let's go to another value. So let's go to the next integer, moving to the right. So that would be a -1. Substituting a -1 into the expression, I'm going to get an output of a -5. So my slope, anywhere where x is -1, I'm going to have a slope of -5. So something still pretty steep, but not quite as steep as the -8 stuff was. So let's go to our next value here. Let's try a 0. Pardon me, that came out of nowhere. So when x is 0, the slope, the output, is going to be a -2. So anywhere x is 0, we'll have a -2. So something not quite as steep as the blue lines, but steeper than a -1. And that's what we get. And finishing off the rounds here, we'll go to a +1. So when I substitute a 1 in there, 3 minus 2 gives me a slope of 1. So here, we just draw little segments that are about a slope of a +1. And a little off on that one. And let's go ahead and take care of the last bit here at a positive 2. So when x is a positive 2, 6 minus 2 gives me a slope of 4. So something fairly, ooh, probably not that steep, but something definitely steeper than the 1, uh, positive going that way. Now, at this point, I want to make sure that I include some general concepts for you here. Oops, go away, I'm not trying to type anything. The, what? Oh, sorry, my hand is touching something it's not supposed to. The slope field, as you can plainly see, the slope field never looks like the expression that you have in your differential equation. And we can make that connection relatively easily because the expression that we have from our differential equation is linear. And the slope field clearly is not made up of a bunch of lines with a slope of 3. So what does it look like? So go ahead and add this to your notes here. The slope field looks like the solution of the differential equation. So what does the solution of this particular differential equation look like? Well, let's go ahead and work it out. Now, what I did on the first example on the last slide, it's going to be pretty similar here. What I'm going to do is I'm going to take the dy over dx. I'm just writing out the differential equation as it was given to me. And I'm going to multiply both sides by dx. We're separating the variables. So, oops, not g. I don't know where I'm getting g from. Erase, please. So I have dy over dx to, oh, golly, I am not thinking clearly. Dy is equal to, in parentheses, 3x minus 2 times dx. There we go. I knew I would get it eventually. So, for our differential equations, when we try to solve them, after we separate the variables, we need to integrate both sides. And that's what we're going to do next. So on the left side, when I integrate dy, the antiderivative of dy is just y. And on the left side, I'm going to get 3 over 2x squared minus 2x plus a constant. Okay. So the slope field, if you look at it, very much looks parabolic. I could kind of draw a parabola that opens up anywhere, kind of looking like somewhere here might be our axis of symmetry. And you can very clearly see that I could take whatever parabola is there and move it vertically up or down. And that's what we say is the family of functions, because C can be kind of any given number. And that's what will cause the quote unquote family to give us different parabolas. They'll have the same characteristics. It's just that, they'll open up higher on the y-axis or lower on the y-axis somewhere. So that is what we have for our first example of slope fields. So now the next one's going to complicate things a little bit, simply because we're going to have two input numbers. Now I want to be clear that this, oops, I don't need my eraser. This is not matching the notes that I'm giving my students for this lesson. The example that the students have says 2x minus y times dy dx is equal to 0. So we're going to go ahead and solve this for dy dx. So I'm going to say negative y times dy dx will be equal to negative 2x, and then divide by the negative y, and we get 2x over y positive. So this is the expression that we will use to identify our slopes for given x and y values. So let's go ahead and try one. Now, you guys are going to need to pause the video at some point to really fill in the slope field because there's simply not enough room on the table for me to do all of the possible points here. But let's try this uppermost left number when x is negative 2 and y is a positive 2. So if I take those numbers and substitute them, 2 times negative 2 is negative 4, divided by 2 will give me a slope of negative 2. Okay, so that will give me a slope of negative 2, something like that. Now let's look at other negative 2 values for x, and let's compare, because in the last example what I did is anywhere x would have been a negative 2, I would have put that slope of negative 2. Well, let's try when x is negative 2 and y is a positive 1. Well, negative 2 times negative 2 gives me, or times positive 2 gives me a negative 4 in the numerator, divided by a positive 1 gives me a slope of negative 4. So this slope here is going to be much steeper than the one directly above it. Well, what happens if we continue going down the column, so to speak, in the negative 2 x values? So let's try negative 2 and 0. Well, we're going to be, it doesn't matter what the numerator is, we're going to be substituting a 0 in the denominator, so that is going to be something that is undefined, meaning that we have a vertical line at that point. Okay, so we've gone from a negative 2 to a negative 4 and eventually to an undefined. So the steepness is changing. So is it going to change now to a positive number if we continue going down? So let's go ahead and try next numbers. Let's try negative 2 and a negative 1. Well, negative 2 over a negative 1, or substituting those numbers, we'll get a negative 4 over a negative 1. So that'll give me a slope of a positive 4. So here I have a slope of a positive 4, something pretty steep. Let's keep going. Let me pick another color here. Let's try this yellowish color. Negative 2 and negative 2. Well, that would simplify to be negative 4 over negative 2, so that would simplify to be a positive 2. So we can't necessarily see where when x is going to be a particular number, in this case, that the slopes are going to be the same for all values of that x number, because the y value definitely has a role to play in determining the value of the slope. But we are able to take advantage of some symmetry that we see in the problem. Okay, so you can see when x was at the extremes at positive 2 and negative 2 for y, we had the same slope, the absolute value, it's just that one was positive, one was negative. Same thing when x was a positive and negative 1, or when y was a positive and negative 1. So I'm going to just add a few more things here, and then I'll fill in the slope field overall. But at this point, if you haven't already done so, pause the video and try to get some more values to fill in your table and finish filling in the slope field. And then when you're done with that, hit play and see does your slope field and my slope field match. Okay, so I'm going to pick a few more numbers here, and I'm going to just kind of keep them all the same color now, because changing the colors is getting a little tedious. So let's try it at positive 1 and positive 1. So when x is 1 and y is 1, that's going to give me a slope of 1. So when x is 1 and y is 1, I have a slope of 1 here. Let's try when y is 1 and or x is 1 and y is 0, that's again going to be something undefined. Okay, so I'll have a vertical line there. And let's try 1 and a negative 1, and that would simplify it to a slope of a negative 2. So at positive 1 and negative 1, I have a slope of a negative 2, something about there. So when we finish filling in the table, the y values are, we are going to have something consistent at the y values. Anytime y is 0, we will have a vertical line, something undefined there, so we can kind of fill those in very quickly. And same thing with x. When x is 0, and I know I didn't do any of those on the table, but when x is 0, the numerator is 0, so the slope is always going to be 0. So anywhere x is 0, the slope will be 0, so we can fill those in pretty quickly. And we'll just have some things that we can kind of see. Let's take a look at the row when y is a positive 1. If you look at negative 1 and positive 1, we're going to have a slope going down like so. And that should match a negative 1 because we had a positive 1 on the other side, because we are going to be seeing some symmetry here. At negative 2 and positive 1, we had a slope of a negative 4. So at a positive 2 and a positive 1, that's going to give us a slope of a positive 4. Okay, so at negative 2 and negative 1, we had a slope of negative 4. I'm sorry, a positive 4, and so at positive 2 and negative 1, that should give me the flip of that. That should be about a negative, uh, what was it, negative 4. So something like so. And they're just going to go ahead and fill in the rest of these here. I'm going to just do them very generically now. So going across the top row, the slopes are going to decrease until we get to that horizontal line, and they increase again. And that's going to kind of be the nature for every row. Here it's going to be decreasing and continue to decrease as we go from left to right. And here it's going to be decreasing, but oops, I missed that completely, but not quite as much. And so there's generically our slope field. And I know I went through and filled that in kind of quickly. I wasn't trying to be very detailed because of time, but you try to do a better job on your notes. So taking a look at example 3, we're kind of looking at the expression here to fill in some values here. So when x is 1 and y is 1, the slope will be a negative 1, and this will give a slope of 1, negative 1, and positive 1. Okay, so dy dx is going to be positive in quadrants 2 and 4. Here this is quadrant 1 because both of the values are negative. Here this is going to be quadrant 2 because x is negative and y is positive. This will be quadrant 3 because x and y are both negative. And this will be quadrant 4 in case anybody's wondering how I'm looking at that. And so the last one, the slope is negative in quadrants 1 and 3. Okay. And this is just trying to illustrate patterns that you'll be able to take advantage of, symmetries that you'll be able to see with lines of reflection. Now here we're still using the same expression. So whenever y is 0, because y is in the denominator, all of these, no matter what the x number is going to be undefined. They're all going to be the same. So here, write an equation that would describe the slope as undefined. Well, with the vertical line, that's when we have x is equal to 0, or x is equal to any number, really. X can be equal to c, any number. And when the slope is 0, that would be when y is equal to some number, or when y is equal to 0, or y is equal to any particular number. That's when we would have a horizontal line with a slope of 0. So in table 3, we're looking at the slopes of positive 1, positive 1 and positive 1 for x and y. That's going to give me a slope of negative 1. Here, again, where this is in quadrant 1, this is in quadrant 1, and we already know that the slopes there are negative. And this is going to be in quadrant 3, and this is going to be in quadrant 3. So again, the slopes are going to be negative, and if you substitute those into the expression that was given to you, the negative x over y, those are the slopes that we wind up getting. What equation would express y is equal to a negative 1? Well, that would be something like y is equal to negative x, something like that. Uh, or it could be y is equal to negative x plus some number to show a vertical shift, and something that would have a slope of a positive 1, that would be like the linear parent function, y is equal to x. Or if you want to show any kind of vertical shifts, you can say y is equal to x plus 1, or x plus c rather. And now, again, at this point here, I definitely want you to attempt to work this out one on your own and see what you wind up getting. We're just taking the expression that we had at the top of example 3. I want you guys to pause the video, answer these questions, and particularly take the time to do the slope field. And when you're when you're done, go ahead and hit play. So part D, I'm assuming that you've paused the video and worked everything out, says to sketch the slope field, and this is by far going to take the most time. So we know in quadrant 2 and 4, we're going to have slopes of positive 1 anytime the x, let's clean that up, anytime the x and y values are going to be the same. And I am not going to try and make this perfectly clear or perfectly detailed, but we know that here at quadrant 1 and 3, when the x and y numbers are the same, we have a slope of a negative 1, so we can fill those in. You can kind of see that anywhere x is 0 as the numerator, anywhere x is 0, we're going to have a slope of 0. So anywhere x is 0, I can put a horizontal line. And anywhere y is 0, that's going to give me something undefined, so I can put a vertical line anywhere y is 0. So that would be the x-axis there. And essentially what you're going to be seeing as we kind of go across is that these slopes, in order to go from a positive slope to a slope of 0 to a slope of a negative 1, the slopes are going to have to be decreasing in some way. And then they're going to continue to decrease until we get to a positive 1. And it's going to kind of work that way across the entire function. And I'm not going to try and illustrate what all of the actual slope values are going to be. But you can kind of take the time to figure them out. This one is a fairly tedious process to work out. Oh, that one's a little too steep. That one's not quite shallow enough. And it's going to look something like that. So what it's telling you to do, it says draw the particular solution that passes through 0, 2. So let's go ahead and identify where 0, 2 is on the function. So 0, 2, something right here. Oh, I don't want to pick the same color. I wanted a different color. Okay. Now, looking at this particular slope field, this is very much circular. So it looks like if it's centered around centered from the origin, I'm going to have a radius of 2. So we're going to have something like so. And we have a circle. So an equation of a circle that has a radius of 2 and is centered around the origin would have an equation of x squared plus y squared, is equal to the radius squared, which would just be 4. So the radius is 2, so 2 squared is 4. Now what we're going to do is we're going to change gears a little bit after I fill in these last little bits here, explain what happens to the values, to the slope values as you move left to right with a fixed y value. So here I'm going to not be as descriptive as I probably would on my own paper. As x increases, and I can't spell, I keep wanting to write a G for some reason. As x increases, dy dx will decrease, and what happens to the slope values as you move up from the x-axis? You can just look at your function, look at your slope field, and see what happens. So here, as y increases, dy dx will approach 0. Now we're going to switch gears a little bit and see, can you match the slope fields to a given function? Okay. Now let me give you guys a little hint here, and go ahead and make sure that you write it down on your paper. Look, look for slope of 0 or a slope that is undefined. Something where I have a horizontal line and a vertical line, because those are going to be kind of our key things here. So let's take a look at example 1. All right. What would make this have a slope of 0? Well, if x was equal to a -2, the radicand would be 0. The square root of 0 is 0. So essentially what I'm going to do, because I only have one input number, x, I'm going to look for a vertical line anywhere I have. Let's just say that this is where x is -2. And looking at A, I can very clearly see I don't have a horizontal line. Same thing here, I don't have a horizontal line. Here I don't have a horizontal line. Now here, this one looks promising. This one doesn't, because there's a whole bunch of x things missing here. Here, I'm getting a whole bunch of slopes that are different. Same thing with G and H. So I am fairly confident, and we'll go ahead and take off these lines here, because I'm just kind of looking to see, where do I have a slope of 0? And the slope of 0 in this case is going to be D. So 1 is D. And I want you guys to go ahead and pause the video now to try and identify the other 7. Look to see where something has a slope of 0 or something that has a slope that's undefined, and see where you can match these up. This will take you probably a minute or 2 to work through. So if you haven't paused the video, we're going to go ahead, or we're going to presume that you've gone ahead and paused the video, so that way we can work through the rest of this. 2 matches with graph A. 3 matches with graph G. 4 matches with graph H. 5 matches with graph E. 6 will go with graph C. 7 matches with B. And 8 will match with graph F. So the last thing that we're going to take a look at is we have a differential equation, and in this case we have a starting value. We have a particular point. We have some initial conditions that are given to us. So we are going to find a particular solution for the differential equation. So I've worked out a couple of these for you, but essentially, again, we want to separate the variables. I want to get the x's on one side and the y's on one side. And so I'm going to multiply both sides by dx, and that'll give me dy will be equal to 1 over x plus 2 times dx. So at this point that we've separated the variables, we are going to integrate both sides. And when we do, the integration of dy, the antiderivative would just be y. And on the right side, the antiderivative of the ratio of the fraction will be 1, because that's what the numerator is, times the natural log of the x plus 2, and plus a constant. Now in this case, we know what the initial conditions are. We know, and so let's go ahead and substitute those, and I'll do that in a different color here. We know that when x is 0, y is 1, so I'm going to substitute 1 for y, and here I'll get natural log of 0 plus 2, which would just be natural log of 2 plus c. So to get c by itself, we're going to say 1 minus the natural log of 2 will be equal to c. So that is the value that we have for c. And that's not going to be a pretty number, so I'm going to just leave it as an exact value there. So here we would get our particular solution is the word they use, to be y is equal to the natural log of x plus 2 plus 1 minus natural log of 2 for c. And that would be so all of this here, the 1 minus natural log of 2, that whole thing is c, and this would be our particular solution. And what would it look like when we sketch it? Well, we know we have to go through 0 and 1. We have to go through that point right there. And this is generally a logarithmic expression. Remember, let me do this in a different color so it doesn't all blend together. But all of this here, you can type this on your calculator. This is just a number. Okay, I'm just leaving it in exact form because I don't want to write out the decimal number. So this is just a function that's been shifted to a log function that's been shifted 2 spaces to the left, and that's very much what we're seeing here. We have a vertical asymptote at about -2. So the function itself is going to follow that logarithmic curve following the absolute value or the vertical asymptote up and then going through, and I'm leveling off a little too much here. I don't like that. Leveling off a little too much, like so. And that's what we would have for our particular solution and the graph. Remember, the slope field looks like the solution of the differential equation, not like the given expression. So here, I'm going to go ahead and try to type these up instead of writing them out because I think I can type a lot faster than I can write. So yes, I want to switch from tablet mode, but I don't want it to be super big. Okay, what strategies could you have? Well, one strategy would be that when you have dy dx, so dy dx has x increasing, slope will change from left to right only. So here, the second thing that we have, dy over dx, when it has y increasing, slopes will change up and down only. the third thing that we can say that if I have dy dx has x and a y, oops, I don't need two commas, slopes will change in both directions. And finally, the last thing that I have to add here, uh, find conditions to make the slope 0 or undefined, because those are very easy to see on the slope field. But that's going to take care of this lesson. I apologize if the length got a little out of hand, but I wanted to try and get this all in one video. But if you have any questions, let me know, contact me, and I'll be happy to answer any questions that you have. But until then, ladies and gentlemen, thanks for watching. Take care, be good, and stay safe.